pretty simple theorem. Theorem 3.7 says in a nutshell, it's a test for concavity. I'll write test for concavity. Okay? And it says let f be a function whose second derivative exists on an open interval I. Let f be a function whose second derivative exists on an open interval I. And that open interval is kind of like that open A comma B thing we talk about, interval we talk about. All right, there are three parts to this. The first part says if f double prime of x is greater than 0 for all x on that interval, if the second derivative is greater than 0, the second derivative represents how the first derivative is changing. And if the second derivative is greater than 0, it means that the first derivative is increasing. So that was our definition of concave up, which means now instead of talking about increasing or decreasing, we can jump that and we can just say a second derivative greater than 0 for all x on an interval indicates that the function is going to be concave up. So I'm going to say then the graph of f is concave up on I. And I'm just going to use the CU for concave up. And the second piece, I'm sure you can come up with yourself. If f double prime of x is less than 0 for all x values on the interval, then the graph of f is concave down on I. Remember, a second derivative is nothing more than the first derivative. So this is a derivative of a derivative, which is the second derivative. So this tells us that we're dealing with the change in the first derivative, or the change in slope. Okay. Alrighty. And finally, if we told you what was happening when f double prime was greater than 0 and less than 0, I'm sure you want to know what's happening when f double prime of x actually equals 0 for all the x's on some open interval. Not just at one point, but for every single value along an open interval between a and b, or whatever your interval happens to be. Then what do you think the graph of f has? Because I'm thinking that if we're not concave up, or we're not concave down, then there can't be any bend to this curve. So it can't really be a curve, so to speak, if we're not curving up or curving down. So in this particular case, then the graph of f is neither concave up nor down. And in parentheses here, I'm just going to say f is linear. So I'm just going to draw some function f, straight line. This is my function f. This function is neither concave up nor is it concave down. And I'll tell you the reason it can't be concave up or can't be concave down is because the change in my slope is not positive nor negative. Or my slope is not increasing or decreasing anywhere. My slope is constant. So the second derivative tells us how the slope is changing. And if the slope is not changing, I must have a linear function. Now the linear function might be increasing, the linear function might be decreasing, or maybe the linear function is a constant function itself. All three of these situations satisfy the fact that the second derivative is equal to 0, and therefore the graph is neither concave up nor concave down. The function f would be linear. All right. I'm going to go ahead and give you the definition for a point of inflection. and then we'll talk about another theorem. So we'll get rid of this. You'll see the definition for a point of inflection change from book to book and from teacher to teacher, but we all have the basic idea of what it is. I think it's kind of hard to put it in a nutshell, but let's go for definition. Okay, and I wrote, if a function f exists at some value c, if a function f exists at some value c, and f changes concavity at x equals c, the c value, of course, an element of the domain, okay, then c comma f of c, so I need the xy coordinate point, c comma f of c is a point of inflection of f. And some people might say of the graph of f, or of the function f, or just of f is where we're going with this. We talk about concavity, we're definitely talking about the graph. Okay, so if you have a function f, and that function has some point within it, not some asymptote, but some point that's actually defined in the function, and at that point the function f changes concavity, maybe we switch from concave up to concave down, maybe we switch from concave down to concave up. It doesn't say which way you have to switch, it doesn't matter which way you switch, as long as the concavity changes right there at that one instant when x is equal to c, then you can take your c, plug it back in as an input value to your original function, get your y coordinate, and this xy coordinate is known as a point of inflection. They will often be asked to find the point of inflection or the points of inflection as opposed to where the point of inflection exists. So they want both the x and the y coordinates most often. Okay, I think I will squeeze this theorem 3.8 right here. It's a pretty simple theorem. It says if c comma f of c, if c f of c is a point of inflection, POI is a typical abbreviation for point of inflection, but we don't call it a POI, we call it a point of inflection. You're allowed to use the abbreviation, but you have to say it, please, okay? So if c f of c is a point of inflection of the graph of f, then either f double prime of c has to equal 0, f double prime of c has to equal 0, or f prime of c is not defined. If f prime of c is not defined, well then f double prime of c is also not defined as well. For some reason in the definition they state f prime of c is not defined in the theorem, I'm sorry. But if the first derivative is not defined, obviously the second one is not going to be defined. Okay, I say this kind of an easy theorem, and it is, but I need you to understand that this theorem goes in one direction and not necessarily in the other. So, and the definition of a point of inflection is typically misstated. If you were to ask almost any calculus student what is a point of inflection, many of them are going to tell you it's where the second derivative is equal to 0. And that's not necessarily true. It's very often true. A point of inflection has a second derivative at that point that's equal to 0. But the definition of a point of inflection is where the function f changes concavity. And it has to not just be a spot someplace on your graph, but it has to be a point that belongs in the original function. So, if you do have a point of inflection, and you know that 3, 2, let's say, is a point of inflection, well then I know that the second derivative at 3 would have to either be 0 or undefined. One or the other. but it's not always equal to 0. We'll get some ideas about that coming up a little bit, and we'll talk about it a little bit more after that. Matter of fact, I can give you right now an idea of something. If I graph for you y equals x to the 4th, if I took that derivative, I would have 4x cubed. If I took that derivative, I would have 12x squared. And 12x squared would be equal to 0 when x is 0. And 0, 0 is a point on this graph. 0, 0. Y equals x to the 4th is pretty flat and pretty straight on both sides of this. I'm not right on top of it, so I can't quite get the symmetry perfectly well for you. I don't know how well I just did there either. But y equals x to the 4th definitely has no point of inflection right here at 0, 0. And yet, the second derivative at 0 is 0. No inflection point, or point of inflection.